Hi, my name's Jordan Wheeler, and today I'm going to show you how to simulate a superconducting resonator in Sonnet. This is an array of kinetic inductance detectors, which are basically superconducting LC resonators. And I'm going to spot check my design, make sure I didn't screw up the pixels by just checking a few random locations here to make sure they are as I expect. So I've previously decided that I'm going to pick number 21 with some random number generator, px121 first. So that's this pixel here, and basically you can see that this is a resonator, so there's an interdigitated capacitor, that's the capacitance of the resonator. There's an inductor over here, which is just a skinny wire, and this is going to be made of aluminum, so there's not only is there geometric inductance from the skinny wire, but also kinetic inductance. And then there's another capacitor here that defines the coupling to a microwave feed line here, which is a microstrip where the ground plane is a wafer that's above this. Okay, so first thing I want to do is grab this pixel and save it to a GDS that I can import into Sonnet. And the way we make these actually is that we have 4 different pixel designs here, but they're basically all the same. And then we set the resonant frequency by trimming the capacitor here with a cutter. So if I turn this to red, you can see, okay, we flash this picture here, and then we expose this cutter to remove some of the fingers to set the resonant frequency. And likewise, I secretly have, I can either do the top or bottom feed line says coupling capacitor here, so you can see that I decided to couple to the bottom feed line here instead of the top by cutting off this top coupling capacitor. But I want all these parts to copy paste over so that I can do the cutting operations like the lithography would. So let's do File, New Layout. Okay, see, did we get everything we need? Looks like it. Okay. All right, so first things first, my actual resonator is these layers 2, 3, 4, and 5, and they're different layers, not for a particular reason here, but in the end they're just all going to be aluminum. So I drew this by drawing a bunch of squares, and I haven't bothered to merge the shapes yet, so I'm going to go ahead and do that now in Klayout. So first I think we need to set it all to the same layer, so edit, selection, change layer. Okay, so now it's all in layer 4. Now we're going to select it again, edit, selection, merge shapes here, merge shapes. Okay, and then after that, this is all now one shape, not a bunch of little squares. And that'll make it easier, a little bit easier on importing the GDS and things like that. The next thing I want to do is I want to kind of do the operations like the lithography is going to do. So the first thing is we're going to wet etch this aluminum, and so I've drawn the lines as 1.3 microns across, but I expect them to end up at like 0.8 microns because the etch is going to eat away a little bit this. So I can just do that in Klayout now, edit, clear all rulers and annotations, so I can just select everything. And then we can go to Edit, Selection, Size Shapes, and here I'm thinking that the wet etch will remove 250 nanometers, minus 250 nanometers from every side of the line. So if we do that, hit OK, and now we see the lines have gotten skinnier. They should be 0.8 now. So that should reflect what it actually looks like when it's made. And then I want to go ahead and let me clear annotations here. I want to go ahead and subtract off the cutter that defines the capacitor like we will do with lithography here. So I can do that by doing a Boolean operation, edit, layer, Boolean operations. So let's do layer 4 minus cutter C3 into layer 4. Okay, and now we can get rid of that. Hide that, and we can see, oops, I don't think I did the right Boolean here. Let's go back, edit, layer, Boolean operations. Okay. So layer 4, cutter 3. We don't want to do union, we want to do A, not B here, difference, into layer 4. Yes, okay. Edit, clear all rulers and annotations. Okay, and then we want to, oh, let's see, we're not going to have a feed line when we get done with this. So maybe, because the feed line is on the bottom of the other one. So let's see if we can just, well, we can draw that on Sonnet later. Okay, so let's go ahead and subtract off this other cutter. So this cutter is getting rid of one of the two coupling capacitors and also defining the number of coupling capacitor fingers here. So again, just do a Boolean operation here. Edit, clear all rulers and annotations. Oh, whoops. Edit, layer, Boolean operations. So let's do layer 4 minus LCC bot into layer 4. Let's hit OK. All right, good. All right, so now we're left with just the resonator that we expect to be made when we actually fabricate it. And so now I want to just say that as to a GDS, file save as. I think that's a fine place to put it. So we'll call this PX121 as a GDS. We'll go ahead and just save the visible layers because all we want is that layer 4. That's going to be the aluminum here. Hit OK. All right, now let me move over to my computer I have Sonnet on, and let's do a new geometry. And we're going to do File. We're going to import that GDS. CKDUR, Fusion 3, edited CS, PX121 here. Open. Sure, copy polygons from template. Top, yes. Okay, we want to convert that into, I guess we'll leave it as unknown metal for the moment. Stream number 4. We want to bring that in, put it on level 0. We'll not add any margins to it. And then we're going to do a manual cell size here. So that's 0.8 micron line width. And because I have a few 45s in there and stuff, I need to do 0.4 microns for my cell size. We can do that now. Oh, not cooperating with me. Oh, we're in mils. Okay, hold on. Before we import, let's go ahead and change our unit settings. Units, microns. That's what we like to think in. Back to File, Import, GDS. Where were we? Version 3. PX121. Open. Next. Top. We want to import number 4. We can do an unknown metal. Okay, manual. Let's see, this will cooperate with me. 0.4. Doesn't like 0.4, does it? Okay, there we go. 0.4, 0.4. Okay, 0.4, 0. Okay, next, let's see how this goes. Okay, so I left the box as some big thing here. Let's go ahead and edit that box. I happen to know that my pixel is 27,500 across. Let's just make it equal in Y as well. Let's go ahead and center this. Object, center both. Okay, and then I need, this is on a silicon substrate. It's actually on a SOE substrate that's 80 microns thick. The relative epsilon of that is 11.7 cryogenically. And then there's an air gap here. This is actually what the ground plane of the microstrip is. There's a 20 micron air gap there that defines the ground plane of the microstrip. Let's see if we can change this metal. Okay, let's make a new metal. Let's call it aluminum. and we want to do general here. And so the special thing about this is superconducting aluminum is going to have a kinetic inductance of about 1 picohenry per square for our 30 nanometer thick aluminum. Okay, so let's do that. Hit OK. OK. Good. And then let's draw the feed line that we deleted off. Draw metal rectangle. Okay, so the height will be I think 37 microns and the width 2750, the size of our box. Did I get in the right spot? A little low, looks like, but on the edge here. Okay, so then let's insert some ports. Port 1. Insert port 2. Okay, and then we have everything. Basically, we need to set up the simulation here, so let's do that first. So sweeps, let's do an adaptive sweep from, now I know I've designed all these to be a half gigahertz to 1 gigahertz, so we'll do 0.4 to 1.2 gigahertz. Hit OK. Now, you know, this has a relatively high Q resonator, so the adaptive sweep might miss the resonance. So actually I'm going to play a game here where I'm going to put an internal port in the middle of the inductor, and where the impedance of that port is 0, we'll know we're on the resonant frequency. And you can also use that port to calculate the Q of the resonator. I'll do the full simulation later, but in order to get, you know, generally the right frequency, I'll do this first. Okay, so what we want to do is place a port right in the middle of the inductor. You know, this design's interesting, so it's not totally obvious where the middle of the inductor is, but I already know that it's basically right here. So I'm going to cut the inductor here and drop a port. Insert port. There we go, port 3. And we better turn this on. We better turn this on faster, less memory, or we're going to spend the rest of our life simulating it, because 0.4 micron grid's pretty small. Okay, so well, this is lossless, shouldn't matter, but we can go ahead and make that aluminum too, eh? Metal 1. Oh, where is our metal 1? Edit. Edit. Interesting. Is this still aluminum? Somehow our metal changed back here. So let's take all the metals. Edit. Oh, only one material at a time. Okay. So what happened to our metal here? Our aluminum we made. There it is. Huh. Why did it do it? Okay, let's change that to aluminum as well. Okay, so let's go ahead and add that to the queue. You want to spec Sonnet? Sure. So we'll put this as PX121. Okay, if we're lucky, we have the license here. We do have the license. I think still this is going to take a little while, so I'll pause and come back to recording more when it finished to show you the results here. Okay, now let's go ahead and take a look at that simulation we ran. I guess first I'll show this. This is the paper that tells you about this trick of putting this third port in the middle of the inductor. So you can look that up for more information. All right, so I ran the thing and basically decided that the adaptive frequency sweep was never going to converge. It just kept trying to fill in more points there. You can see it just filled in a bunch of points. But, you know, from this, I can basically get an idea where the resonant frequency was anyway. I did want the adaptive sweep to converge, so I just ended up running another sweep zoomed in on where the resonant frequency is, which is basically where the impedance of this is going to 0. You can kind of also see it by looking at where the imaginary part of this crosses 0, because and the real impedance is the real part of this is very small. So I basically knew the resonant frequency is here, so then I went ahead and ran it again, but zoomed on in just on those frequencies. And let's see, let's take a look at that. Okay, so a graph. All right, we want to look at the Z parameter for port 3. And okay, basically, whoops, we got too many things here. Let's delete that one. Just Z33. And basically this is showing us that, where this is 0, that's going to be our resonant frequency. So we're finding a resonant frequency of 0.584 gigahertz. And I believe, let's see, I was expecting 0.587. Okay, so that's in the ballpark. So nothing's big is screwed up right there. And then we can also determine the Q of the resonance from this wide sweep. So let's add another one. I'm going to add an axis, and there's a user equation here, Q, which I'll go into. But basically this computes the Q, and you basically just have to find where the resonant frequency, wherever the resonant frequency is, you look at this user equation Q, and then you basically read off that axis Q here. So if I look at this, and I go over here, I see that I'm getting a Q of 43,000 here. And that's basically kind of what I expected. I was aiming for a Q of 40,000, but I only take integer fingers off for the coupling capacitor. So whether I'm, 45,000 or 35,000 might depend a little bit on whether I take one finger or one more finger or one less finger. Let me show you this user equation. Let's see, so how do we do that? Graph, user equations. Okay, edit. All right, so here is the user equation that allows you to determine the Q from this third port method. Okay, so, but of course, I don't expect anyone to believe me that that works. The paper should convince you that it works if you look up the paper, but just to convince you, let's go ahead and remove this port. Delete. Command X. And let's go ahead and make sure we already zoomed in on it, 5.8 to 0.56. So let's go back to that graph here. Is that going to work for us? Sure, 5.8 to 0.6 here. We'll just go to 0.9. Because now that we're trying to zoom in on the resonance, we don't want to miss it. So settings, 0.59. Okay, for some reason whenever I change anything here, it seems to reset this metal type. Not sure why that is. Let's put it back to aluminum. Okay, and then let's file, save as, no internal. I will go ahead and add that to the queue, and we'll have a look at that, and we can confirm that we get the same resonant frequency and the same Q when that finishes. Okay, and then we'll have a look at that when it's all done here. Okay, so I went ahead, that simulation went ahead and finished, and basically when I looked at it, I saw that I hadn't zoomed in enough to be able to actually resolve the Q of the resonator, so I went ahead and readjusted the adaptive frequency sweep to zoom in even more. So here's the new frequencies. We could take a look at that in the plot here. That's S11. Let's look at S21. Okay, all right, there's our resonator. And the first thing we can see is did we get basically the right resonant frequency? So this is coming out at 5843, and then before our answer was coming out at 5845. So basically we're right in the right ballpark there, maybe off a little tiny bit. And then the other thing we want to check is the Q. And so let's go to the 3 dB point here. 3 dB point is there. So that's 584322. Then let's see if we can go to the other 3 dB point. There we are. So that's 584,309. Okay, so 22 minus 09 is 13. Okay, so let's calculate the Q. So that'd be F over delta F. So F is 0.5843 divided by 0.000013. Okay, and we get a Q of 45,000 here. And so let's check if that makes sense with what we got with our internal port. So the internal port was basically telling us that the Q was 43,000. So basically pretty darn close. And so that gives you the basics of how to simulate a superconducting resonator. Here we haven't put any losses in this resonator, so the loss is really low. So this Q is not the internal Q at all, it's just the coupling Q, the strength of coupling to the feed line, right? So that was determined by this little interdigitated capacitor, right? Here, the number of fingers there determines the strength of this coupling and the Q that we measure with the Sonnet simulation. And then the resonant frequency is determined by the inductance here and the capacitance here. Great, so thanks for listening.